Students, welcome back students. Today we will see the transmission line equations and we will derive the solution of the transmission line equations. So first of all, as we know that the two-wire transmission line or a two-conductor transmission line supports the TEM wave. It means that the E and H field on the line are perpendicular to each other and transverse to the direction of the propagation. So, as we know, the property of the TM wave is that the E and H field are uniquely related with the V and I. So, we know that for that case, V can be expressed as minus E dot dl and I can be related as per the Ampere's law H dot dl. So, as we can express the transmission line as in terms of the voltage and current, so instead of using the field quantity E and H, we will use the circuit model, and which is simple and more convenient. So for solution of the Maxwell equations involves the three space variables and the time variables, while if we use the distributed circuit theory, then it involves only one space variable in addition to the time. So for getting the transmission line equations, you will use the distributed circuit theory. So our objective here is to get or to find the equivalent circuit of the line. And to derive the equations, transmission line equation. So for that case, let us first of all model the two conductor transmission line as a L-type equivalent circuit. So as we know that in a transmission line we have mainly the four parameters R, L, C and G. So we can represent its equivalent model in terms of the L type as so in this case we have used let us first draw the equivalent L-type model of the transmission line. Which consists of the mainly four transmission line parameters that we have seen. So here this one is considered as a small differential R element. So if we have considered the small amount of the incremental length of the transmission line as a Z, for example this one is our point Z, and if we consider this part as a z plus small incremental change delta z, then for this case this equivalent r parameter can be represented as a r delta z. Same way I can express this inductance part as a L delta Z. So it is nothing but the small incremental change of the inductance. Same way we have two other G delta Z and the C delta Z. So I can say that this one is a typical L type equivalent equivalent model, transmission line model. So there are other way also to express the models, but here we have used the L type equivalent circuit model. Here we have assumed the wave propagation direction is in a z direction. So this part I can consider as a towards the load, while this part I can consider as towards the generator. So if I applied any voltage at the source side, then the voltage at this point I can express as the V z comma t, while because of this voltage the current which is flowing through this line I can express as I z comma t over this line. So at this point I can consider the current as I z plus delta z comma t. Same way I can express the voltage at this point as the V z plus delta z comma t. So this way now we have expressed the voltage and currents at a different point on the transmission line. Now let us apply a KCL and the KVL for obtaining the equivalent circuit of the line and for deriving the transmission line equations. First of all, we will apply a KVL over this loop. So if we use the Kirchhoff's voltage law around this loop, then we can write the instantaneous voltage as V z comma t, that is equal to the voltage which is dropped across these two components plus the voltage of these sections. So I can write equivalent equations as the current I z of t r delta z plus the voltage drop across these inductor can be expressed as L delta Z di by dt. So differential of the Iz comma Z by dt plus now the drop across this. So V Z plus delta Z comma t. So I can express this one as a equation number 1. So now we have a KVL relations. So let me rearrange this equation is in a such a way that, or I can express as now minus, so I put this part over left side so that minus V Z plus delta Z comma t minus V Z comma t over delta Z, that is equal to R Z plus L del I Z by dt. So now I have such a relations where if I take the limit, so taking the limit delta Z tends to 0, then I can express this as the differential relation, which is nothing but the minus del V Z comma del t over del Z, and that is equal to R IZT plus L del I Z comma t over del t. Or I can express this relation as also, because here we are omitting now this space variable and time variable, because no need to write each and every time Z comma t. So I can express as minus del V by del Z is equal to R I plus L del I by del t. So this is our one of the transmission line equations that we will use for obtaining the final transmission line equations. Now similarly, for obtaining the second relations, we will apply a KCL. So earlier we have used the KVL at starting loop. Now we will apply the KCL at this point. So here you can see that the current which is flowing at this point is nothing but the IZ comma t is equal to the IZ plus delta ZT plus delta I. So delta I is the current which is flowing through this branch. So now let us try to get the relation or equations of that KCL. So at this point, if we will write the KCL, then by applying the KCL, we will get the Iz, t, as I mentioned, is nothing but equal to Iz plus delta z, t plus delta I. So now I can express this delta I as nothing but current which is flowing through this line and current which is flowing through this line. So if you sum up these two current, for example I1 and I2, then we can say the delta I as I1 plus I2. So let me now try to write down that part. Then I can write that Iz plus delta z, t plus delta IA is nothing but the G delta Z and the voltage, which is nothing but the resistance and the voltage, which is nothing but the Vz plus delta Z T. So voltage across this resistance into the resistance, that will become the final current. So I can write that the G delta Z, V Z plus delta Z, T. So this is the first current I1 which is flowing through this conductance G part. Now same way the other current I2 I can express as, which is nothing but the current flowing through this capacitor branch, then C delta Z del V Z plus delta Z, T over del T. So finally I have a current relations which actually can be expressed also as, so let me once again write down the same thing in a different way. So minus I Z plus delta Z T minus I Z T over delta Z, and that is equal to the G V Z plus delta Z, T plus the C del V Z plus delta Z, T over delta T. So let me write down the same thing in another page so that you will have a let me write down once again the same expression as minus I Z plus delta Z, T minus I Z, T divided by the delta Z, that is equal to G V Z plus delta Z, T plus C del V Z plus delta Z, T divided by delta T. So if I now take once again the limit. So taking the limit delta z tends to 0, then I will get minus del I z comma t over del z, and that is equal to gv z comma t plus c del v z comma t over del t. Or I can write the same thing here as minus del I over del z is equal to gv plus c del v by del t. So ultimately now I have a equation number, this I can consider as a 3. Earlier I obtained the equation number 2. Here you can see this is nothing but our equation number 2. So finally we have a two differential equations which actually express the transmission line. So now using these two, equation number 2 and 3, where equation 2 can be considered as a differential equation of the voltage and the equation number 3 can be considered as a differential equation of the current. So using these two differential equations, we will try to find out a single one equations which actually express as the transmission line equations. So for that case, let us first assume that here the voltage and the current that are used are the in terms of the variable space and the time, but if we will use some harmonic time dependency so that we will can express the same voltage and current which are earlier expressed as in terms of the space variable and the time, now we will use equivalently as the time harmonic dependent voltage and current. So we will now try to express the voltage and current in terms of the phasor forms, or I can say that in terms of the frequency domain, so that in most of the transmission line problems we are dealing with the in terms of the frequencies. So we want to generally find out the idea about the different transmission line at some different frequencies. So for that we need a transmission line equations in terms of the phasor form or a frequency domains. So for that case, let us first derive the relation between the voltage and currents in terms of the space and time variables and in terms of the harmonic time dependency. So if we assume the time harmonic dependency so that I can express this voltage and current which are in terms of the space variables and the time variable as real part of the Vs of z e raised to j omega t. Same way, current can be expressed as Iz comma t is equal to the real part of the Is of z e raised to j omega t, where Vs of z can be expressed as the phasor form of V z comma t, while the Is of z can be considered as a phasor form of the Iz comma t. So the same equations which was earlier 2 and 3, now in terms of the phasor expressions I can express as minus dvs over dz, that is equal to r plus j omega l in bracket Is. Same way I can express for a voltage case minus dis over dz, that is equal to g plus j omega c and Vs. So now this way we have two expressions. One is in terms of the voltage and one is in terms of the current, which are now in a frequency domain. So let us now try to get out of these two equations. You will try to find out the one common transmission line equations. So here you can see that in these two equations I can eliminate one equations by simply deriving any one of the equations. For example, if I differentiate these equations, voltage equations, then I will get here in the double differential form and I will get here dis by dz. So what will happen, that the same expressions I can put over in this and I can get the single one equations. So let us do that part. So let us differentiate the equation 2 with respect to z, then we will get the minus d square vs over dz square, and that is equal to r plus j omega l dis over dz. So I will use the same equations over the equation 3. So now we have in the equation, earlier equation 3 was dis over dz, that is equal to g plus j omega c over vs. This is the equation 3. So now let me put this value dis over dz over this equation number 4. So by putting the equation 3 into 4, we have minus d square Vs over dz square, that is equal to r plus j omega L into g plus j omega c into Vs. So finally we have a single one transmission line equations in terms of the phasor voltage Vs. Same way, if I do the for a current part, then current can be written as del square Is over del z square, that is equal to r plus j omega L g plus j omega c into Is. So in short, now we have a two transmission line equations. One is in terms of the voltage and one is in terms of the current. So if now have to find out the voltage and current at any point on the line, then either we can use these frequency domain relations, or we can use the time and space equations. As we have now the transmission line equations in terms of the phasor voltage. Now let us introduce the one of the very important transmission line parameter. It is called the propagation constant, and which is generally denoted as a gamma. So here I have introduced now the gamma square is equal to r plus j omega L plus j omega c. So now we can define the propagation constant gamma is nothing but the square root of the whole this term. So if I now replace this full term is equal to gamma square, then the same transmission line equation will become in this fashion. So let me once again rewrite the equation as del square Vs by dz square minus gamma square Vs is equal to 0. So these final equations can be considered as a transmission line wave equations in terms of the propagation constant gamma, where this propagation constant gamma can be expressed as the alpha plus j beta, and that is equal to square root of the r plus j omega L and multiply by g plus j omega c. So finally we have one very important parameter of a transmission line, which is nothing but a complex number. Here the alpha can be considered as the attenuation constant, where the beta is called the phase constant of the line. Generally the alpha is measured in unit the Napier per meter square. So I can consider that alpha is having a unit in terms of the Napier per meter square, while beta can be have a unit which is in terms of the radian per meter. So we can consider that any line can be characterized by the propagation constant. So each and every line has its own unique propagation constant. So now let us see the another parameter, and it is called the wave velocity. So wave velocity can be defined as the u, which is nothing but I can express as a wave velocity, then that can be defined as the omega by beta, where omega is nothing but the angular frequency while beta is nothing but the phase constant. And the same wave velocity can be expressed as the f into lambda, where f is nothing but the operating frequency and the lambda is the wavelength. So this way now we have seen the two important parameters. One is called the propagation constant and second one is called the wave velocity of a transmission line. So now let us find out the very first the solution of these equations. So let us see the solution of these double differential equations. Let us now find out the solution of a transmission line equations. So now our objective here is to find out the solution of this transmission line, which is in terms of the gamma propagation constant. So as you can see that this equation is a linear homogeneous differential equations, and if we will solve these equations, then we will get the two solution of these double differential equations. So solution of these equations is nothing but Vs of z, that is equal to V0 plus e raised to minus gamma z plus V0 minus e raised to plus gamma z. After looking the transmission line equations and its solutions, here we can conclude that there are mainly the two solutions. There are mainly the two waves. One wave is moving away from the origin and it is in a positive z direction, and there is another wave which is also moving from the origin and it is moving in a minus z directions. So here in a positive direction, the wave which is moving is having a voltage amplitude is equal to V0 plus, and as its propagation constant is gamma and the direction is positive, we will get the e raised to minus gamma z. While for a second solution where V0 minus is nothing but the wave amplitude of the wave which is moving towards the minus z directions, and the propagation constant gamma, but here the direction is in a minus z, so we are getting the positive sign. So ultimately we can conclude that there are mainly two waves which composite, and finally we will obtain the one solution of these transmission line equations, where one is moving in a positive z direction and one is moving in a negative z direction. Same way we can consider that if we will try to obtain the solution of a current, then current will also having a two component. One is in a positive z direction component, one is in a negative z direction component. So once we have the wave amplitude either in terms of the voltage or either in terms of the current, then we will finally obtain the solution of this transmission line equations either in terms of the voltage or either in terms of the current. So sometimes if you have to find out the solution of the transmission line equations in terms of the instantaneous voltage, then we have to once again apply our time harmonic dependency. And for this case, if you will define that instantaneous voltage Vz comma t, and that is nothing but equal to the real part of the Vs of z into e raised to j omega t. This part we have already seen. So if you will use this relation and if you will try to solve, then we will get the instantaneous voltage that will be equal to V0 plus e raised to minus gamma z cos omega t minus beta z plus V0 minus e raised to plus gamma z cos omega t plus beta z. So this way we can obtain the instantaneous voltage over a line for it at any space and at any time using these equations. Same way we can express the current also. So in this way we have now the solution of the transmission line equations. Now let us